One math equation could cause reality itself to break down, and no one knows how to stop it. In this video, you'll discover 10 mind-blowing takeaways from Terence Tao's deep dive with Lex Fridman, including one that changes everything. Takeaway 1. This equation could destroy reality itself. Terence Tao talks about one of the most famous open problems in mathematics, the Navier-Stokes equations. These equations are used to model how fluids move, like air in the sky or water in the ocean. On the surface, they seem harmless, but Tao explains that hidden within these equations is a terrifying question. Could they lead to a situation where everything explodes into infinite energy in a finite amount of time? If the answer is yes, then the equation, in theory, could represent a system that grows so rapidly and uncontrollably that it tears itself apart. Tao says that the reason this problem is so tricky is because the balance between calm behavior and wild chaos shifts at small scales. In 3 dimensions, things get unpredictable, and tiny changes can grow into massive disturbances. This is not just a math puzzle. It touches real-world systems, from weather to jet engines. For example, a tiny swirl in a weather model that is not accurately captured might suddenly grow into a major storm if the equation allows for that kind of blow-up. Tao explores whether these kinds of infinite behaviors are even possible under the laws of mathematics. He also imagines a version of the universe made of fluid, where computations happen inside the flow itself. If such a system could shrink forever, copying itself into smaller and smaller versions, it might cause a chain reaction of shrinking and exploding structures. This is how a simple equation, if not well understood, could lead to a complete breakdown of physical reality in the model. It sounds like science fiction, but it is real mathematics at the cutting edge. Now let's move to the next takeaway. Takeaway 2, a computer made of water is possible. In a mind-bending part of the podcast, Terence Tao explains that in theory, it is possible to create a computer out of nothing but flowing water. This idea is not science fiction. It is based on the fact that the laws of fluid motion can be controlled to perform logical operations, just like how computers use electricity to do math. Tao says that by designing specific fluid patterns that act like AND or OR logic gates, you could make a liquid Turing machine. This type of computer would be able to calculate anything that a regular computer can, but instead of using wires and chips, it would use tunnels and currents. The problem is that building such a system is incredibly difficult in practice. It would require perfect conditions and exact control of the flow, which is nearly impossible with real-world fluids. But as a thought experiment, it is powerful. For example, Tao imagines a structure that can build a smaller copy of itself inside the fluid. That smaller version can then build another, even smaller copy, and so on. If energy keeps transferring into these smaller scales, the system could reach infinite speed or pressure in finite time. This is another way the Navier-Stokes equations might hide a mathematical blow-up. These ideas are not just about showing off clever thinking. They could help unlock new insights into turbulence, weather, or how nature itself processes information. Now let's move to the next takeaway. Takeaway 3, how mathematicians deal with hard problems. Terence Tao shares that truly hard math problems are not just difficult to solve. They sit on the edge of what we understand and push the limits of the tools we have. A problem might be solved in most situations, but the real challenge is proving it in every case without fail. For example, the Kakeya problem starts with a simple question about rotating a needle in the smallest space. But when mathematicians tried to answer it, they discovered connections to geometry, analysis, and even physics. This is common in math. A problem that looks small often hides a deeper world of ideas. Tao explains that in math, something is not considered fully solved until every possible exception is covered. That is why the Navier-Stokes equation is not just about what usually happens. It is about whether blow-up is ever possible, even once. For example, a rare event that almost never happens in nature could still be enough to make the equation unsolvable in theory. Mathematicians want full certainty, not just a good guess. That is what makes these problems so hard and also so interesting. Now let's move to the next takeaway. Takeaway 4, math shows us how the world behaves. Terence Tao explains that mathematics, physics, and reality each live in their own space, but they constantly interact. Math is the world of logical structures built entirely in the mind. Physics takes tools from math to build models of how the universe works. Reality is what we actually experience, which is often messier than the math or the models. Tao says that in math, you start with assumptions and ask what follows from them logically. In physics, you often work backward. You start with what you want to achieve, like building a bridge or launching a rocket, and then ask what equations will get you there. These different ways of thinking sometimes lead to tension. For example, early astronomers thought the Earth was flat because that was how it looked. But as they gathered more accurate data, they had to change the model. Math helps sharpen these models until they match what we observe. Tao says this back and forth between math and reality is what drives discovery. Now let's move to the next takeaway. Takeaway 5, infinity can be both useful and dangerous. Terence Tao talks about how infinity is used in math to make complex problems easier to work with. Even though nothing in the real world is truly infinite, pretending that something continues forever can help mathematicians prove things with more clarity. For example, by imagining an infinite sequence of digits, you can prove that patterns will always appear eventually. But there is a catch. Working with infinity can lead to wrong answers if not handled carefully. Summing up infinite series or rearranging infinite terms can give misleading results. Tao says there is now a growing interest in converting infinite proofs into finite ones. This is useful for making arguments easier to understand and more practical. For example, instead of imagining monkeys typing forever and eventually writing the works of Shakespeare, a mathematician might ask how many monkeys and how much time it would take just to write one sonnet. This makes the idea more concrete and avoids the traps that come with infinity. We're halfway through the video. Thanks for sticking with us. If you're enjoying it, hit the thumbs up and share it in your WhatsApp groups. If you'd like to support us, please tap the thanks button below. It helps us keep making great content. Drop a comment and don't forget to hit subscribe for more. Now let's continue with the video. Takeaway 6, math might be behind everything we see. Lex Fridman and Terence Tao explore the idea that the entire universe might be built from math. Tao says this might be true because of a concept called universality. This means that even very different systems tend to follow the same basic patterns when looked at from far enough away. For example, you do not need to track every air molecule in a room to understand the temperature. You just need a few average measurements. This is what makes statistical models so powerful. However, Tao warns that when people trust the math too much without understanding the assumptions behind it, things can go very wrong. For example, in the 2008 financial crisis, experts used mathematical models to predict how safe certain investments were. But the models assumed that mortgage failures would be random and unconnected. In reality, when one group defaulted, many others followed, and the system collapsed. This shows that while math is incredibly powerful, it can also be dangerously misleading if used without proper understanding. Now let's move to the next takeaway. Takeaway 7. AI might soon help us discover math. Terence Tao talks about how artificial intelligence could change the way math is explored. In the past, math was done by proving ideas step by step using logic. But now with the help of computers, people are starting to look for patterns by running simulations and generating lots of examples. Tao compares this to chess engines, which have completely changed how people study the game. These engines do not explore every possible move, but they still find powerful strategies that surprise even top human players. For example, an AI might suggest a chess move that seems bad to humans, but turns out to be brilliant after many steps. In the same way, AI might find strange patterns in number theory or geometry that no one has noticed before. Mathematicians could then try to prove these patterns using traditional methods. This partnership between humans and machines might lead to entirely new ways of doing math. Now let's move to the next takeaway. Takeaway 8. Tao visualizes problems in strange ways. Terence Tao shares how his mind works when solving difficult problems. He often uses imagination and physical intuition, rather than just symbols and equations. In one case, he lay down on the floor, closed his eyes, and tried to imagine himself being part of a vector field, just to feel how it behaves. This kind of thinking helps him connect with abstract problems in a deeper way. He also uses a trick called strategic simplification. This means changing the problem slightly to make it easier to understand. For example, he might first pretend that an equation is one-dimensional instead of three-dimensional, or that a difficult term is zero for now. Once he understands the simpler version, he slowly adds the complexity back in. This helps him see the overall structure before diving into the messy details. It is a reminder that great thinkers often solve hard problems by finding playful and creative ways to look at them. Now let's move to the next takeaway. Takeaway 9. Good math proofs feel like clean code. Terence Tao believes that a good math proof is not just about being correct. It should also be beautiful, clear, and reusable. He compares writing proofs to writing clean computer code. A messy proof might work, but it will be hard for others to follow or build on. Tao recalls a talk by mathematician John Conway, who said that proofs exist in a kind of space where some are simpler, shorter, or more elegant than others. Tao tries to write proofs that help people understand why something is true, not just show that it is. For example, there are many ways to prove that there are infinitely many prime numbers. Some are quick and clever, others are long and deep. The best ones make you feel like you have learned something new, not just reached the right answer. Now let's move to the last takeaway. Takeaway 10. Great math connects unexpected ideas. At the end of the podcast, Terence Tao explains that the most beautiful part of mathematics is how different ideas suddenly connect in surprising ways. One example is Euler's identity, which links imaginary numbers, rotation, and exponential growth in a single elegant equation. What makes it special is not just the result, but the fact that it brings together concepts from completely different areas of math. Tao says that many fields in math were once separate, like geometry and algebra. But thinkers like Descartes helped unite them by showing that you can describe shapes with numbers. Tao enjoys moving between these different worlds and finding hidden connections. For example, a trick from number theory might help solve a problem in fluid mechanics. These strange links are not just clever. They often lead to new discoveries and open doors to deeper understanding. Here is a brief introduction about Terence Tao. Terence Tao is a world-renowned mathematician often called the Mozart of Math for his extraordinary early genius and groundbreaking work. He has made major contributions across fields like number theory, fluid dynamics, harmonic analysis, and mathematical physics, and is a recipient of the prestigious Fields Medal. Thank you for watching. If you'd like to support this channel, hit the thanks button below. It really helps us keep going. If you enjoyed this summary, please leave a like and share it in your WhatsApp groups. To join discussion about this video, drop a comment below. And for more videos like this, hit the subscribe button below.